contemporary landscape of engineering simulations, a myriad of methodologies are deployed to address problem ranging from rudimentary to profoundly intricate. For complex issues, the selection of an appropriate simulation method is paramount, as the accuracy of the solution is contingent upon this choice. Notably, computational fluid dynamics simulation often employ Eulerian and Lagrangian method, both widely employed in fluid mechanics studies. As collective students, our mandate is to undertake a case study utilizing both Eulerian and Lagrangian method in CFD simulations to model the spray and combustion processes within a diesel engine. This video encapsulates the outcome of this comparative investigation. In the realm of diesel engines, where efficiency and emission controls are pivotal, the accurate prediction of spray and combustion processes proved to be an intricate challenge. In this context, Eulerian and Lagrangian methods emerged as prevalent choices for CFD simulations. The focal issues revolve around discerning the efficacy of this method in modeling the complex interaction inherent in diesel engine combustion. The primary concern is to gauge their performance against one another in simulating real-world diesel engine behavior, thereby contributing to the optimization of combustion processes.
Assalamualaikum, my name is Aiman Rais. Basically, my metric number is 2140806. Okay, for our objective of this case study is to develop a comprehensive computational fluid dynamic safety model that accurately simulates the spray and combustion process occurring within a diesel engine. Specifically, this study aims to integrate both Eulerian and Lagrangian method to enhance the accuracy and efficiency of simulation, providing a detailed understanding of the complex interaction between fuel, spray, air, and combustion products. Okay, we have 6 primary objectives. That is to implementing Eulerian method to simulate the microscopic behavior of the fuel air mixture within the engine. We also want to utilizing Lagrangian method to track individual fuel droplets, considering the trajectories, interaction, and microfuel. We also want to integrate both Eulerian and Lagrangian frameworks to model the combustion process within the diesel engine. Then we want to validate the safety model against experimental data to ensure its accuracy and reliability. Lastly, we want to evaluate the impact of proposed optimization of the efficiency, emission, and overall engine performance. Okay, for the methodology that we want to use for this case study is first we want to conduct a true review of existing literature to understand the current state of knowledge regarding the diesel engines, combustion, and spray modeling. Basically, we want to understand how the diesel engines and spray modeling work so that we can make the 3D modeling and do a true review about this safety model using both the Eulerian and Lagrangian method. Then we want to develop a detailed 3D geometry of diesel engine, combustion chamber, and associated component. To use that, we want to use safety software that support both Eulerian and Lagrangian method for multi-phase flow, so that we can see the detail and get the data that we needed to understand this case study. Okay, next we want to set up the Eulerian framework to simulate the continuous phase of the fuel droplets for the fuel emission capturing microscopic flow characteristics. Then we want to implement a Lagrangian particle tracking for individual fuel droplet, considering factors such as size, distribution, initial condition, and backup model. Then we want to integrate both Eulerian and Lagrangian method framework to simulate the combustion process, so that we can analyze both method that we want to know which one is the best to know the data about this case study. Then we will validate the entire safety model against every available data for spray and combustion process.
Assalamualaikum, very good afternoon to Dr. Aziz. Now I would like to continue with result and discussion. In this case study is the combination of Eulerian and Lagrangian method. So as you can see from here, the velocity field show the impact of shield motion on gas movement. The evolution of the spray, including ISO line of total liquid volume fraction, showed change in the spray contours and penetration under different conditions. Observe included the effect of autoignition on gas temperature and evaporation rate, and the impact of engine fuel on spray deflection. Then phase droplet diameter were analyzed, showing the effects of separation, evaporation, and thermal expansion. As you can see from the picture 2 shows the thermal expansion of 710 degree crack angle and 720 degree crack angle. Then gas temperature were compared before and during combustion, highlighting the agreement between engine and spray client and the effective evolution of combustion on temperature. As you can see from the picture 1 shows the inside part of the picture 1 is the Eulerian method, and outside of the picture 1 is the Lagrangian method. Then Eulerian method and Lagrangian method has few difference. Eulerian method more effective in dense spray region where the flow field's global view is crucial. It handles the collective behavior of numerical particles, but it has one limitation, that is less effective in tracking the movement of individual particle, which can be crucial in delayed spray region or for detailed particle path analysis. Then on the other hand, Lagrangian method is ideal for problem where tracing individual particle trajectories is important, such as in the light speed region, but it also has a limitation, that is, Lagrangian method can become less effective in dense speed region where interaction between numerical particles become complex, and this difference we find out from this case study. As you can see, the picture one is the phase change from Euclidean method to Lagrangian method, and the picture 2 shows the outlier particles of Lagrangian method. That would be all from me. Thank you.
In conclusion, this comprehensive study has elucidated the comparative merits of Eulerian and Lagrangian methods in the simulation of spray and combustion processes within diesel engines. The intricacies of each method was scrutinized, revealing that Eulerian, with its microscopic orientation, adeptly capture overarching combustion characteristics. In contrast, Lagrangian methods, functioning as a meticulous observer, provide detailed insight into the behavior and spatial distribution of fluid droplet. The selection between this method is contingent upon specific simulation pool and available computational resources. Consequently, the insight garnered from the study served as a valuable guide for future CNT simulations, fostering advancement in diesel engine optimization and emission reduction. That is all from us. Thank you.